I am Dr. C. Christie, Assistant Professor from PG and Research Department of Computer Science, St.Joseph's College of Arts and Science, Autonomous, Cuddalore 1. This video lecture, let us see about trees from a fundamentals of data structure. Table of contents. Introduction to trees. What makes trees unique? Understanding nodes. Children and siblings in trees. Degree of a node. Calculating degree of a tree. Defining ancestors and descendants. Identifying leaf and non-terminal nodes. Understanding levels in trees. Exploring height and depth. Conclusion. Introduction to trees. It is a non-linear data structure. It has a finite set of one or more nodes such that a special designated node called root. The remaining nodes are partitioned into n disjoint sets T1, T2 up to Tn, where each set is a tree. T1, T2 up to Tn are called subtrees of the root. This example, A is the root node, B, C, D are children of the root node A. Like that, E, F are children or branches of node B. H, I, J are branches or children of node D. What makes trees unique? The root node serves as the main entry point, while other nodes branch off into children, creating a structured hierarchy. Each node can have one or more child nodes, establishing a parent-child relationship, a key characteristic of trees. Unlike linear data structures, trees allow for a more complex representation of data relationships. This structure is important for databases, file systems, and network architectures. Understanding nodes. A node represents a single piece of information and can connect to other nodes, forming a network of data. In our example, node A acts as the root, connecting to various child nodes such as B, C, and D. Each node's ability to branch out is fundamental for creating vast interconnected data frameworks. Nodes are the building blocks of all tree structures, defining the flow of information. Here, the root node A, it has branches B, C, and D. These are direct connection to node A. Like that, M is the node, that is the branch from H. It has direct connection to node H. Children and siblings entries. Children are the immediate subnodes of any given node directly connected to it. For instance, in example tree structure, B, C, and D are children of node A, shows a direct relationship. Siblings are nodes sharing the same parent, highlighting the detailed connections within the tree framework. Understanding these relationships is key to navigating tree structures efficiently. In this example, B, C, D are the branches of same parent A. So, B, C, D are called siblings. The same way, H, I, and J are children for parent or root node D. So, H, I, and J are called siblings. Degree of a node. The degree of a node refers to the number of direct connections it has. Node A with 3 children, so it has degree of 3. While node B with 2 children, it has degree of node 2. The same way, the node D has 3 children, so the degree of node D is 3. This property helps to analyze the complexity and branching nature of trees. This example clearly shows how degrees vary across nodes, affecting their hierarchical position. Calculating degree of a tree. The degree of a tree is determined by the node with the highest degree within it. Identifying the maximum degree helps in understanding the tree's complexity and structure. In our example, the highest degree is observed is for node A 3. The same way node D, which dictates the tree's branching capacity. This metric is essential for optimizing algorithms that traverse tree structures. Defining ancestors and descendants. Ancestors are nodes found on the path from a particular node up to the root, representing lineage in trees. This concept is vital in understanding hierarchical relationships within tree structures. Conversely, descendants are the child nodes stemming from a given node, shows data flow. Recognizing these relationships facilitates data categorization and retrieval processes. Identifying leaf and non-terminal nodes. Leaf nodes or terminal nodes are those with no children, indicating the end of a branch. In our example structure, nodes such as F, G, I and J are terminal, highlighting their isolation in terms of connections. Non-terminal nodes like A, B and C have one or more children, emphasizing their role in data branching. Understanding this distinction aids in designing efficient data queries and algorithms. Understanding levels in trees. Levels in a tree structure refers to the hierarchical position of nodes starting from the root. For instance, the root A is at level 1, while its children B, C and D are at level 2. The same way, E, F, G, H, I and J are at level 3 and so on. This structure aids in visualizing and managing data effectively, especially in large data sets. Recognizing levels simplifies understanding the depth of information contained within a tree. Exploring height and depth. The height or depth of a tree is defined as the maximum level present within it. In our example, the tree's height is determined by the furthest leaf node from the root. Understanding height and depth is vital for analyzing tree performance in data retrieval and storage. Optimizing tree height can lead to significantly faster data access times, enhancing overall efficiency. In this example, the level of the tree is 4. A is at level 1, B, C, D are at level 2, E, F, G, H and I, J are at level 3, K, L and M are at level 4. So, the height and depth of this example tree is 4. Conclusion. Trees are integral to understanding complex relationships, offering a versatile structure for representation. Key concepts like nodes, degrees and levels facilitate effective data management and retrieval. Recognizing these principles can significantly enhance your approach to data structures in computer science. Mastering trees not only improves technical skills but also promote innovation in data-oriented applications. Thank you for participating in this exploration of trees as a fundamental data structure. I hope this presentation has provided you with invaluable insights into tree structures. Feel free to reach out with any questions or further discussions in this topic. Happy learning and exploring the world of data structures.